So welcome everyone for another CAP seminar. Today we have Elisa Delgado Mena. She got her PhD in 2011 from the Instituto of Astrofísica de Canarias y la Universidad de La Laguna in the Canary Island, focusing on the chemical abundances of elements like lithium, beryllium, carbon, and oxygen in exoplanet hosting stars, and on how planet formation affects these elements. After that, she conducted her research through the Fundação para a Ciência e Tecnologia Postdoctoral Fellowship at the Centro de Astrofísica da Universidade do Porto. And later, she got 2 research contracts on that center and the Instituto de Astrofísica de Ciencias do Espacio. In 2024, she started her Ramon y Cajal Fellowship at CAP, and her main research interests include the derivation of stellar chemical abundances for solar-type planet hosting and M-dwarf stars, exoplanet detection and characterization, especially around evolved stars, stellar activity and atmospheres, and the chemical evolution of the galaxy.
Okay, thank you.
Thank you.
So thanks for the presentation and for the invitation. Can you hear well? Yes? Okay. As he said in the presentation, I'm going to talk about stellar abundances. Although this is not the only thing that I have been working. Indeed, in the last times, I dedicated more time to the search for exoplanets around the evolved stars. But in this talk, I will really focus only on stellar composition. Okay, so first of all, why are stellar abundances important? They are important for a number of topics in astrophysics. So you need to know the stellar abundances in order to know about the formation of the galaxy. Should I move the microphone? No? Okay. Then it's also important to understand the nucleosynthesis processes in the galaxy, so how the elements are formed, where and when. Then you also need the stellar abundances to be able to classify your stellar population, so to distinguish between the thick and the thin disk, the halo, the bulge, but also to try to put stars together as born in the same place through the chemical tagging technique, for example, where you can put stars in the same association or open cluster. Then having chemical abundances can help and can complement the studies on asteroseismology and stellar activity. And it's also important to help constraining the distances and to complement the studies on, to derive the H's and to complement the studies to constrain the distances. And last but not least, it's very important to have a well characterization of your stars in order to detect and characterize the exoplanets that they host. So in this talk, I'm going to focus on these 2 topics. The first one, which is the galactic chemical evolution, and the second one is the star-planet connection. Then after that, I will give you a brief overview of how we get the abundances from the stellar spectra, and I will show you some examples. And finally, I will briefly explain the challenges we are facing now in terms of stellar abundances. Okay, so let's start with the first topic, the galactic chemical evolution. So it's important to know the chemical abundances at different scales in order to know the events that produce these elements. For example, here I'm showing the composition of the Earth's crust and the universe, the current universe. You see, they are very different. So to know how we pass from one to the other, we have to study the chemical elements in different stars, in different populations, to understand all the events that give that made going from one step to the next one. So this is what galactic chemical evolution studies. So all this change of events that produces the elements in different sites in the galaxy. So the first elements were created in the primordial nucleosynthesis. This is something that happened just a few seconds to minutes after the Big Bang. In this process, all the hydrogen and most of the helium in the universe was created together with some traces of deuterium and lithium. So then, where are the rest of the elements? Where do they come from? So the answer is in the stars, through stellar nucleosynthesis. So at the very beginning, there were a population of stars called population 3 that were very massive stars, up to 1,000 solar masses, that have very short lifetimes, just 1 megayear, that release the first metals into the universe. And then after this first generation of stars, successive generations created the rest of the elements as we know them today. Maybe you have seen this periodic table with all the processes that are involved in the production of elements. It's a very good summary. So then you have, so there's blue ones that I mentioned from the Big Bang nucleosynthesis, but then there are others that I created by cosmic ray fission, like beryllium. Many others are in exploding massive stars. Others are produced in low mass stars. And then each of these processes have a different time scale, as I will show now. So to be able to reach to all this information that we have in this table, we needed a lot of studies in different populations of stars. And these studies started to pop up at the early 90s, because it's when we started to have more high-resolution spectrographs, and we were able to study bigger samples of stars. So this is one of these first works where there were 200 FG-type stars studied. And this is the abundances of alpha elements with respect to iron versus metallicity. In this talk, I will be talking about metallicity, but when we are talking about solar type stars, metallicity usually means iron abundance, because it's one of the easiest elements to determine in this kind of stars, and also it correlates well with metallicity for this population of stars. And it's also a proxy for age, as we will see later. So as you go backward in metallicity, then you go backward in older times. In other fields in astrophysics, for example, they use oxygen as a tracer of metallicity. So then these plots, what it's telling us is that the alpha elements with respect to iron are positive. So they are higher, they are enhanced with respect to iron as the time goes back. Later, with more studies, with higher resolution, we were able not only to see this increasing trend towards lower metallicities, but also the distinction of the populations. So all these stars that are here that have enhanced alpha abundances are the thick disk. The ones that are below is the thin disk. And then this study allowed for the first time the discovery of this new population, which is called high alpha metal-rich stars. So they are stars, it's not clear whether they are extension of the thick disk at higher metallicities or they are a different population that maybe migrated from the inner galaxy. So how these elements are formed? The first thing we have is the massive stars, the ones that release earlier their elements in the universe because they have shorter lifetimes. So as the massive stars evolve, they start to fuse more and more elements inside in the interiors. So they end up their lives with this kind of layer shape with a lot of layers with different elements. So then you have the products of this fusion. So you have carbon, oxygen, neon, magnesium, silicon, up to iron. When this chain of reactions, nuclear reactions reach to iron, you cannot fuse more because you will need energy instead of producing it. And at this moment is when the star finishes its life and explodes. So, but before this happens, so all these elements that have been created, here, they will be released into the interstellar medium and be used in next generations of stars. On the other hand, for the production of iron peak elements, so it's iron, nickel, cobalt, manganese, vanadium, these are mainly produced in binary systems of low mass stars. It says when a exploding white dwarf that is around another secondary star, then when this happens, all these elements are released. So this is what explains this behavior here, what is called the knee. At older times, the massive stars have started earlier to produce these alpha elements, which are the alpha elements are successive fusion of a helium nucleus. So this is all these elements that I say: magnesium, silicon, titanium, calcium. So at earlier ages, because only massive stars were releasing elements in the universe, then in the interstellar medium, you have higher alpha over iron. And then around solar metallicity, these two processes balance, and then you start to have a similar abundance of alpha elements and iron peak elements. So if in addition to the abundances, you add the stellar ages, then you will have a much more insightful view on galactic archaeology, what is called galactic archaeology. In the last year, there have been a lot of studies because there were bigger surveys in different telescopes like LEMOS, Apogee, Kepler, the Gaia ISO survey, GALA, that they have collected thousands, even millions of stars. So then we have a very good broad view of the full galaxy. So we have stars at different positions, some of them very far away, And then this has given us a global picture of the situation. And then we were able to distinguish all these kind of four kind of elements, so the alpha elements, the iron peak elements, and then the neutron capture that I will talk about now. However, even if these super big surveys are needed and are very important, the problem is that since they are focused on farther stars and also they have a lower resolution, they don't have enough precision to trace some elements. And this is why it's still important to continue observing in the solar neighborhood with high resolution and high signal to noise spectra. And when I mean high resolution, I mean above 50,000. But ideally, 100,000 is when you can start to see some specific lines that I will show you later. And this is something that I have been doing with some colleagues in the last years. I think this was the first paper that, as I explained before, they were showing this population of high alpha metal-rich stars. And we were studying specifically the HARP CTO sample, which is a survey that was done in La Silla, in the 3.6 meters telescope in La Silla. HARPS is a very stable spectrograph, which is designed to discover exoplanets. And then there was a survey in the solar neighborhood. It's a volume-limited sample, around 60 parsecs from the sun. And then we have very high signal-to-noise ratio spectra because since it has been searching for exoplanets, we can co-add a lot of individual spectra to reach a higher signal-to-noise. So then we have around 1,000 stars, which are divided in these different populations. And these pink ones are the halo stars that are farther away. We have also studied the heavier elements, which are the neutron capture elements that I mentioned before. For the first time also, we were able to see some trends, for example, zinc abundances, which is part of it created similar as the alpha elements. It has also a bit of increase towards lower metallicities, and then you see very well separation between the thick disk, the thin disk, and the high alpha metal-rich stars. Also for copper, you see this distinction. And then on the other hand, you have these S-process elements, slow neutron capture elements like barium, strontium, which have a different behavior. They reach the maximum abundance around solar metallicity. And this other element is different, it's europium. Instead of being a slow process, it's rapid process. A neutron capture element is created in a different way. And this shows a more similar way as the similar behavior as the alpha elements. So these kind of studies are important in the solar neighborhood because they also serve to test models, especially at higher metallicities. So many of these models indeed don't reach to these higher metallicities because they didn't have data to test with. And how are these S-process elements formed? They are formed in low mass stars. So when the stars evolve out of the main sequence, when they finish the hydrogen in the nucleus, they go through the red giant branch, and they ascend it, and then they start to burn helium in the core here. This is the red clamp. And once they exhaust the helium in the core, and they have a carbon-oxygen core, they go up this track, which is called the asymptotic giant branch. And towards the end, these stars suffer like thermal pulses in the exterior envelope. And then there is a flux of neutrons that through neutron capture, the seeds of iron produce these neutron capture elements, these yttrium, barium, lanthanum, which sound a bit like exotic, although they are used for some industrial purposes, and they are also important for the ages, as I will explain now later. On the other hand, when the massive stars finish their lives, when they reach to this nucleus of iron, they explode as a supernovae because the star collapses. It cannot sustain itself, it explodes as a supernova type 2. And then it releases the elements that I showed before that were created previously in the interior. But at the same time, there is also explosive nucleosynthesis, which is different than the stellar nucleosynthesis. And then these rapid neutron capture elements are produced like europium. And this, you can see here, this is a figure, a plot of a supernova. So when they explode, they are really even brighter than the hosting galaxy. But also in the last years, thanks especially to the observations of LIGO, it has been shown that these rapid process elements, the very heavy elements, can also be produced in neutron stars collisions, in mergers. And you can also produce radioactive elements like thorium, uranium, and also other heavier elements like golden or silver, etc. In this HARP CTO sample that we have used to derive a lot of different elements, we have also derived the stellar ages with isochrons. which is not the best method to derive ages, but not as good as asteroismology, for example, but this is what we have right now. So we were deriving ages, and then, well, this is something that it has also been studied in other works. You see the relation of iron or metallicity with the age. There is a general trend, so as you go to older ages, the metallicities are smaller, but there is a big dispersion. So in reality, metallicity is not as good proxy for age as we believe, or we used to believe, even if we are considering here stars only that have a very small error in age. However, the alpha over iron abundances have a much tighter correlation with age, so they are a better proxy. And here you can see the plot that I showed before, so alpha over iron respect to iron, respect to metallicity, with a color scale of age. So you can see these are the thick disk stars that are much older in red. Then for the thin disk, you can see the youngest ones, which are the purple points. These are the ones that have the lowest alpha abundances. And then for a fixed metallicity, as you go up, as you go to higher alpha abundances, then you start to increase the age. And then you have here these square symbols that are these high alpha metal rich stars, which are different from the thin disk stars. So they are older and are alpha enhanced. So all these differences, these tiny differences and distinction between the population, we were able to do it because of these high precision and studies with the solar neighborhood sample. Okay, so now we can move to the star-planet connection. I don't know, sorry, 1 second. Yes, I thought I missed a slide. About the ages, just one important thing that we can also use the ages to estimate. Sorry, we can also use the chemical abundances to estimate the ages of the stars. Because what I told you about these different time scales for the production of the elements, you can use these different abundance ratios, which are also called chemical clocks, to try to infer the stellar ages. So, for example, you have, for example, zinc. Increases, the abundance of zinc increases towards older ages. However, for the case of barium or yttrium, it's the opposite. You have higher abundances as the stars are younger, which are the purple points. But you can see also that there is a dependence with metallicity. So this is the abundance versus metallicity and the age in color, or this is the other way around. You have the abundance versus the age and the metallicity in a different color. So we can create empirical calibrations, but also even with more complex methods, including a lot of chemical clocks with machine learning, we can infer the ages from these abundances. This works very well in the solar neighborhood, but you have to be careful if you want to apply this to regions farther from the solar neighborhood, because there is also a correlation with the galactocentric radius. For example, if you want to test the ages in open clusters that are far away. Okay, and now, yes, we move to the star-planet connection. So once we know how the elements are formed and how the environment, how is the environment where the stars are formed, we can start to understand also how the planets are formed and what is the imprint of these abundances on the planets, on the different planets born in different parts of the galaxy. Because the planets are formed in the same protoplanetary cloud as the stars. So in principle, it's logical to think that the composition of the star will be imprinted in the planet, right? This is the starting point. And well, I'm showing here just to let you know that today there are more than 6,000 exoplanets discovered. You can see this cumulative. There was a big jump, especially after Kepler. And then depending on the method to discovery, then you have bigger samples, right? So for example, the transit method has discovered a lot of exoplanets, but the radial velocity, I think it has more. You can see also that this is mass versus period, depending on the detection technique. You can track different regions in this mass period diagram. The good thing of the radial velocities, which are these green points, is that they give us a lot of spectra, of high resolution spectra. And this is what we have been using in our case to study the chemical abundances. And this spectra is important to better characterize the stars. Indeed, maybe you have heard a lot about planets discovered with transits like TESS or Kepler, but usually they have to be confirmed with radial velocities to discard false positives, and also to better characterize the star. The problem is that many of these exoplanets are very faint, and then it's harder to have high resolution spectroscopy. So since the first studies on exoplanets, when there were still 10 or 20 exoplanets discovered, it was this paper, Val Gonzalez, 1997, that already saw that there was a correlation. So the stars that were hosting planets have a higher metallicity than the stars that didn't host exoplanets. And this is explained by the core accretion theory that forms planets, because then you need a higher amount of metals to form your planets, to form the cores in order to then have the accretion later and produce the exoplanets. And this trend was later confirmed, and this is a very well-established correlation with bigger samples. You can see here, no? This is the fraction of stars with planets, that how it increases with metallicity. And here there is the difference of two distributions. So this is the stars hosting exoplanets, and this is the metallicities of the single stars. And you can see clearly how they are bigger, they are larger. As the techniques improve, we started to discover lower mass exoplanets, Neptunians and super-Earths. And in this case, it's not so clear the correlation. For example, both from transits and radial velocities. You have here the Kepler, small radii hosts. And in red, these are in red. And you see that the metallicity distribution is similar to the one of the single stars or solar neighborhood stars. Also with radial velocities, for example, this cumulative diagram, this is the stars hosting Jupiters, which have a larger metallicity. However, there are two lines here overplotted. These are the single stars and the Neptunian hosts. So they have more similar metallicities. So once we study the metallicity with the iron, then we say, okay, and the natural step, the next natural step is to study other elements. So can we find differences in other elements in these stars? And the answer is yes. At the beginning, it was a bit complicated because the samples were not big enough. It was a mix. So what they were calling comparison stars, they haven't been searched for exoplanets. So it was not sure if they have at least giant exoplanets. But later with this HARP GTO sample, we were able to show for the first time with a significant trend that the stars hosting exoplanets have higher alpha over iron abundances. These are the red are the Jupiters, and the triangles, the blue triangles, are the Neptunian hosts and super-Earths. So the reason for this is probably that if you don't have enough iron, then you need to compensate it with other elements like magnesium, silicon, oxygen, which we know indeed that they are very important for the formation of exoplanets, at least rocky exoplanets or the core of exoplanets. We have also tried to see if other elements present any kind of correlation. We found, for example, no, this is magnesium, aluminium, that also show enhanced abundances, while titanium is one of the alpha elements. We also tested with the heavier elements. We found, for example, that zinc is overabundant in planet hosts. But of course, this doesn't mean that all the elements are important or they are higher because they are important for planet formation, just because they share a common origin in the case of zinc, no? Which is a very, not very abundant element in the Earth, for example. So elements that share a common origin, then they will have a similar behavior. We have also studied carbon and oxygen that are very important as well for planet formation, especially for giant exoplanets. They can tell us about how the exoplanets will form. These elements are a bit more complicated because they cannot be measured in cool stars, in stars cooler than 4,500 or 5,000, depending Kelvin. So we have less stars, but we also found a tentative evidence that also, this is at the borderline of being significant, that also these planet hosts at lower metallicities have enhanced carbon abundances. And mixing carbon and oxygen, then we can study also the carbon to oxygen ratios that are important, for example, to determine the ice lines in the protoplanetary disks. But again, we have to be careful with the abundances, how we derive them, because they are very dependent sometimes on the spectral lines that you use. I will show you later some examples. But this is the CO ratio using two different oxygen lines. And you see that with one of them, there is a large dispersion. You reach very high values of CO that are not realistic. And then you have a strong dependence with the temperature, which is these color scales. So cooler stars have larger ratios. However, if you use this other line, which is more difficult to measure, unfortunately, then you have less dispersion and a more clear trend. Okay, so when you discover exoplanets, ideally you would have transit and radial velocity, and then you can have the density because you have both the radius and the mass. And then you can have this nice diagram, which a lot of discovered exoplanets back in 2018. But then these lines are the composition of the exoplanets, no? So these ones are the ice giants. Then you start to have here the terrestrial planets. These are stars rocky, no, that have silicate. And then as you go down, then with higher density, then you will have the planets that are pure iron, like, for example, we'll have Mercury. And here you can see the Venus and Earth. However, for a same density, you can have different compositions. And to try to break this degeneracy, we can use the stellar abundances. This was probably the first study. It was a pioneering work by Bond et al. In 2010 that used stellar abundances to try to guess how would be the planetary embryos around those stars. And then through n-body dynamical and chemical simulations, they managed to construct how these hypothetical planets would be and the composition they would have, which are these diagrams that you see here. And then depending on the stellar abundances, you can form very different kind of exoplanets and at different distances. So you can really have a broad range of compositions and different from the Earth. So there is the idea that these carbon, oxygen, and magnesium silicon ratios can be used from the stars to infer the composition of the exoplanets. In this diagram, I'm showing these two ratios. They are important because they control the mineralogy in the rocky exoplanets. So the carbon over oxygen controls the distribution of silicon among carbides and oxides. And then on the other hand, the magnesium silicon controls the distribution of silicates, different forms of silicates depending on the amount of magnesium and silicon that you have. The problem of the carbon to oxygen ratio is that it can be very different in the disk with respect to the star, because these are volatile elements, and depending on the distance to the star, it can be in gas form or in ice. However, the iron over magnesium and the iron over silicon, or magnesium over silicon, since they are refractory elements, they condense at much closer to the star. This is a more stable ratio. And indeed, in the solar system, it has been shown that this iron, magnesium, and iron silicon, it's very similar between the Sun, Mars, Venus, and the Earth. So if in the solar system we have a similar ratio between the Sun and the planets, then we can extrapolate this to other extrasolar planets and use these ratios to constrain the internal composition. This is done with very basic models in which you assume that your exoplanet has a core formed by an iron and an iron alloy, which can be nickel or sulfur. Then you add a mantle, form of silicates, and then you can have in your model a layer of ice, water, or both. These are the basic models in which they input, apart from the mass and the radius, they input these abundances to better understand the structure of these exoplanets. There have been several works trying to study this connection between the stars and the exoplanets and see if we can really use the stellar abundances as a direct proxy of the bulk composition. For example, in this work in the left, what they did was to calculate the core mass fraction of the stars, which is in purple, using just the stellar abundances. And in orange, they calculated the core mass fraction of the exoplanets based on models just with the radius and the mass of the exoplanet, considering this very basic model in which you have iron in the core and silicates in the mantle. And what they found is that in general, the compositions of the star and the exoplanets are quite similar, except in the cases where you have very dense exoplanets like this one. And they pointed out that probably this is a supermercury because it has a much higher core mass fraction than the star. So it really has, it's heavier, it has more quantity of iron. This was also done in this other study in which I also participated. So we were using stars with mass and radius determinations with an error smaller than 30%, and we were analyzing homogeneously and very carefully the abundances of all these elements. And then we were calculating the iron mass fraction of the star and the iron mass fraction of the planet, considering only the mass and the radius. And then we saw that there is a correlation, which you can see here, but it's not a one-to-one. So the iron mass fraction of the star, it has a smaller range than the iron mass fraction of the exoplanets. And then you can see here this group of planets that they are believed to be supermercuries, or they are candidates to be supermercuries, which have a very high iron fraction of the planet, but not of the star, not so much of the star. Okay, and with these abundances, you can also do not only in terms of individual analysis of a given exoplanet, understand its composition, but also as a global picture of how will be the possible exoplanets that you can form in the galaxy. Because at different parts of the galaxy, at different metallicities, different ages, you have different abundances of different elements, then your protoplanetary or your building blocks will have a different composition. So in this study, what we did is with a simple stoichiometric model using the abundances of iron, magnesium, silicon, carbon, and oxygen. We calculated the the core mass fractions, the water mass fraction, and the total metallicity. And what was very clear is that for the water mass fraction, which is this one, the thick disk stars, which are the light blue, have a much larger water fraction than the thin disk stars, which are the white ones. Most of the planets are discovered around thin disk stars. But then these planets in the thick disk are those ones that I mentioned before that have enhanced abundances of alpha elements. And this is normal, this is expected because in the thick disk you have these higher amounts of oxygen, and oxygen is what is forming water. So then it's kind of expected that you will have this. So maybe you can find more water-rich planets, exoplanets in the thick disk because you have these higher values. Then on the other hand, when you see the iron fraction, then of course in the thin disk, which is this one, you have a larger value. This study has been also done later by other authors in which they were using a bit more complex model, but the idea is similar. They use abundances from the GALA survey. And in this case, they separated the compounds they will have in the protoplanetary embryos or building blocks outside and inside the CO line. And they found that this water mass fraction outside the CO line also decreases as the metallicity increases. Or if you have a low metallicity, then you will have much higher water mass fraction. So you see that also these abundances serve to understand in terms of population, the full galaxy, what kind of exoplanets can we form. But also these abundances, so the planet formation is not only affected by stellar abundances, but also the exoplanets can affect stellar abundances themselves, so the other way. And this can clearly, or they can be easily seen with the specific kind of elements that are the light elements, which are very sensitive to changes in the envelope, because they can be burned very easily, like lithium. And there have been different kind of studies. In one of them, for example, they were studying lithium in exoplanet host stars around solar analogs. And we were finding that most of these exoplanets are depleted in lithium, only in this specific range of solar analogs, which are around 5,600, 5,900 Kelvin. And there seems to be, so the stars that have a higher mass, the exoplanets that are higher, around those stars, the lithium is smaller. It's more depleted. This has also been shown also in a more recent paper in which they were comparing the lithium abundances between planets and non-planets, and they also saw this depletion. And this is believed to because it can be caused by different processes, maybe during the planet formation, because of the disk around the star, there is a change in the angular momentum history, and then this can affect the rotational mixing, which can destroy lithium. But also you can have episodic accretion of material falling into the star, and this can also create lithium destruction. On the other hand, when the stars evolve and they reach to the giant phase, the lithium should be destroyed, because as the stars evolve, after the first dredge up, all the lithium that was in the upper envelope is destroyed through mixing, and then you are not expected to find lithium. But there are some stars that have high abundances of lithium. These are called lithium-rich giants. Most of this lithium is probably created through internal mechanism and a connection between the interior of the star and the outside. But also there are some theories that say that this enhancement of lithium can be caused by planet engulfment. Which is not a crazy idea, because as the stars evolve and they grow in radius, then they can attract their planets into them, and they can engulf these exoplanets, which can, for a short time, in terms of the lifetime of the stars, they can again reach the lithium. Okay, so now I will show you some specific examples of how is the spectra that we use and which kind of lines we can measure. So you don't see only points in the plots, but you also see how is the actual spectra. So to derive the abundances, we need these basic ingredients. So of course, a stellar spectrum. You need a model atmosphere for your star to know the temperature, the pressure. Then you need a line list for your atomic and molecular lines. So you need to know the atomic data, the strength of the lines. And finally, you need a radiative transfer code. There are many of these in the literature and different ways of doing it. And also from the classical methods to derive abundances, so just using the spectrum itself, no machine learning involved, Then you have the equivalent width method, in which you analyze the curve of growth, so how the equivalent width increases with the abundance, or better, the abundance, how it increases with increase of the equivalent width. And then you have a spectral synthesis, in which you create a full synthetic spectrum and you compare it to your observation. So for the first method, you need to have clean lines, so lines that are not very blended and are well separated. And here is what I was saying about the high resolution is important. You see that this is just, I cannot see well the numbers. This is just 5 angstroms, this range, and you have all these lines there. This is a Harp's spectrum. So then if you have a lower resolution, you will not be able to resolve this line, which is a carbon line. Or this one, which is another one in the sun. And it's not a weak line, it's 30 or 20 milliangstroms, so this is a line that can be well measured. Then, of course, you have stronger lines, for example, this line of yttrium, which is one of these elements that is used for the chemical clocks. But again, for this specific line, if you have a fast rotator or you have a lower resolution spectrum, you will not be able to separate these two components. So that's why you also need high resolution. Then you have even stronger lines. If they are very strong, they are not good because then they saturate and then you cannot apply this method. But then, for example, this one that are barium lines, these are affected by hyperfine splitting. So here you don't have a single line, you have a lot of individual components, and you have also to consider this for your derivation of abundances. Then the other method is the spectral synthesis. This is used mostly when you have a more complex region with blended lines, when you have molecules, and then it's better to use this method to model the full shape of the spectrum. So for example, these are sulfur lines that are 2 of them, and then this is good to do a spectral synthesis. This is also sulfur. And then this is lithium. In this case, there are 2 components. It's a doublet, and it's not a symmetric line. You cannot fit it with a Gaussian. And there are tricky elements like oxygen that I mentioned before. This is the best line we have in the sun, at least for our spectrum, because there are stronger lines, the oxygen triplet at 700 nanometers, but this is not covered, for example, by HARPS or other high-resolution spectra. So we have to use this line, which is called the forbidden line oxygen, at 6,300. You see, it's very weak. In the sun, this line is around 3 milliangstrom, and it's blended with nickel. So it's complicated to measure it. This spectrum that has so good signal-to-noise is a coaddition of 78 individual spectrum to reach a signal-to-noise of 650 for a solar type star. You can see here the difference. The orange will be an individual spectrum, and then the black is the coadded one. And another tricky thing of this line is that there is exactly an oxygen air glow that affects this line. It's a line that is created in the Earth's atmosphere. So we have to be careful when we are coadding a spectrum to not have these ones, because if you miss them and you combine all your spectrum, then you will have an underabundance line of, it will be a smaller, no, it will be weaker the line, and you will have an underabundance of oxygen. On top of that, it can also be contaminated by tellurics, for example. I don't show here the telluric, but it will be a strong line here, which is also created by the atmosphere. So you have to remove this spectrum. So the black is with tellurics, the red is without tellurics. Otherwise, you will have an overabundance of oxygen. And because this line is very weak, even these small differences can have an impact on your composition. And then this is an important element for planetary interiors, for example. So it's good to have as much precise as possible abundances. This is the other line I mentioned before that has a lower dispersion, but you see it's very weak. This one is below 2 milliangstroms in the sun. So you really need very high resolution, very high signal-to-noise spectra to be able to measure it. Okay, just to end, I will briefly mention the challenges we have now, which are the M dwarfs. You realize that I was talking only about FGK stars. But then when you go to the M dwarfs, everything is a mess. Because so these stars are very cool and they have a lot of molecules. In the optical, it's impossible to get an individual abundance because all the continuum is depressed by strong molecular bands. You can try to get parameters, but not abundances. And then in the last years, there have been more studies going to the near infrared, because in the near infrared, there is less line blending, there are less molecules, at least in some of the bands, not in all. This was the first study using the CRIRES spectra back in 2012. And then you see here that you can have some of the lines that are individualized, no? And you can measure the abundances and parameters. When you go to the H band, which is around 1500 nanometers, Then there is a big difference between cool stars like the black one and the red one. This difference in 1000 Kelvin produces this strong depression of the continuum due to water bands. So then this complicates the analysis of this spectra. Fortunately, as I said, there are a number of high-resolution spectrographs in the near-infrared that have started to work in the last years, and then we will be able to get better abundances. There was this very interesting study in 2022 to show you the complication of these stars, in which different groups analyzed the same stars with their own techniques. It was using Carmen's spectra. So each of these columns is a different star, and each of these points within the column is different measurements of temperature by the different groups. So for the temperatures, the agreement is more or less good, but for the metallicities, it's a mess. So then this has strong implications, because if you don't know the metallicities, you will not be able also to derive good abundances. And also, for example, you cannot know for sure this planet metallicity correlation if it works for M dwarfs or not, because the metallicities are not in the same scale. Still, the perspectives are very good. Some individual studies have been able some studies have been able to derive individual abundances of some elements, but the errors are still very large. For example, this is the plot that I showed you before, magnesium over iron respect to iron. The dots are the solar neighborhood stars, so FGK stars, but then for the M's, you see these very big errors. And this is something that has been shown also with, I will show you now the plot. This is some regions using spectral synthesis, and for example, this one with Spiro, which is in the Canadian telescope. They saw how this spectral synthetic spectra that is pre-computed. There are many elements, there are many lines that don't show there. So the blue is the model and the red is the spectra. So there is a lack also of atomic data for these stars. And here I saw other two examples using Carmenes and Llano B, which is in La Palma, in which they were deriving abundances of magnesium, silicon for a number of stars and benchmark stars. And then you can see the dispersion is large, or here you can see the behavior of magnesium and silicon in the end dwarfs with respect to the FGK star. So still there is a lot of work to do, but the perspectives are good, and I think with these near-infrared spectra, we will be able in the future to get better abundances. And okay, I end up with the conclusions. So I hope I convince you that it's very important to have high precision, and this is possible when you are studying solar neighborhood stars, especially. The chemical composition of the protostellar cloud conditions the formation of exoplanets. So there is a minimum amount of metals that you need to form exoplanets. But also on the other way around, the planets can affect the abundances of the stars in some cases through these light elements. Then in order to characterize your exoplanets, you need to know very well your star, not only the stellar parameters, but also the abundances. And in order to have significant trends and to understand well the populations, it's very important to have homogeneous analysis and having good comparison samples. So when you are talking about the stars without exoplanets, don't take single stars from the literature. Take stars that have been surveyed previously and they didn't find giant planets. So at least you can say that there were no giant exoplanets there. And finally, well, as I mentioned about the end dwarfs, there are promising results, but still we need improvement in the models and in the line lists. And that's all. Thank you.
Thank you so much, Elisa. Thank you for the talk. Does anyone have questions?
Thanks, Elisa. Really, really nice talk. I have one question regarding the disengulfment of giant planets to increase the lithium abundance. How they have to be very massive for you to measure them, the increase, isn't it?
Yeah. So
doesn't give you some kind of limit on
it was the calculations they will need it kind of Jupiter-sized planets, but there is a limit. So they found that with this engulfment, they can reach maximum values of 1.5. Other studies show up to 2 lithium. So you cannot explain these super lithium-rich giants that reach to 3 or 3.5 or even 4. These ones, the lithium have to be created through the Cameron-Fowler mechanism, that is something that happens inside of the stars, or the hot bottom burning, that is a mechanism that happens towards the AGD, in which you have lithium that is produced in the interior, and then there is a connection between the outer envelope and the inside. Sorry, beryllium is created, and then beryllium is rapidly transport to the stellar envelope, and then it decays to lithium, and then you can preserve it. But yes, you cannot explain all these cases just with the engulfment of exoplanets, only up to a certain quantity.
Yeah, and there's another question I don't understand very clearly. Where you showed the solar system planets and the solar system iron fraction, these just to derive to get a handle of that one.
This
that
one.
Yeah. So you have a change in the fraction of the planet of iron between Mars and Mercury of about a factor of 4 almost, or 3. And so how does it relate? I mean, you get the iron from the star.
Yeah, so you see, for the star is the same because they have the same star.
So how accurate is your determination? You have the solar system, and you know that you could infer anything between 70% and 20%, depending on the planet. So
yes.
So
I don't know the errors for the solar system. Indeed, I would say these values are not calculated. I don't think they are calculated in the same way. They are put there as a reference, but I don't think they are calculated in the same way as the blue points, because the blue points are calculated in the y-axis using just the mass and the radius of the exoplanets. And probably maybe these mass fractions come from measurements in the solar system. This I don't know. I don't know how they were taking these measurements.
Yeah. So how many planets as Mercury you have detected outside?
Yes. So these ones, of course, you have the errors in the mass and the radius, but I mean they are quite distant. So they are very heavy. They're very dense exoplanets. This is a population that was not expected because there are very few candidates discovered. About these supermercuries, there are different theories to explain their formation. They call them supermercuries because they are bigger than Mercury, or otherwise we will not be able to detect them. But even with the errors, so they have really a big mass, so a big density. So that's why they believe they are maybe built of more of iron, pure iron.
Okay.
To be able to explain the high density.
Okay, and the last one I promise, what was it? For the sun, for instance, there's been a huge controversy about the oxygen abundance for a long while because this neighboring thing, and there was a discrepancy between the people doing this kind of analysis you're doing and the people doing astroseismology. So how many of your stars can do the same game and test what kind of composition they should have using the astroseismology and whether they are compatible with the abundances you're deriving from the spectral analysis?
So what we do is that we don't care about absolute abundances because you cannot know. So the absolute abundance depends first on the atomic line list you use and how you measure it, and if you apply NLT or not, 3D modeling, whatever. So we always say that we talk in relative terms. When I show all these plots, these plots with the different populations, like this one, these are all relative abundances to the sun as we measure it. So what we do is to take a solar spectrum of Vesta or other asteroid taken with HARPS, with the same resolution, and we apply the same technique to the sun and to our stars. And then we do this differential, so even line by line. So then we can say that this exoplanet has an oxygen abundances with respect to the sun as we measure of 0.5x or 0.05. And then if you want to translate this into absolute abundance ratios, then you transform them using the solar reference you want. You can use the Asplund abundances or Greves or whatever you want to use, or Loders. And then you put the things in the same scale if you want to compare to other works or, yeah.
So thank you, Paco. Victor, please.
Hi, very nice presentation. Yeah, I have a question regarding the analysis of M dwarfs at the end of the presentation. So you show that different groups analyzing the same stars get the same results, more or less consistent results in terms of temperature, but not so in metallicities. that there is quite dispersion. What is do these groups use the same data, or
Well,
is
yes,
analysis process?
they're the same, but the analysis is very different. There are groups here using machine learning based on pseudo-equivalent weights.
Okay, so is it
Others they are doing deep learning. Others they are doing spectral synthesis, in which they have to take into account log G, for example, the gravity. There is a big degeneracy between metallicity, gravity, and temperature. You can have the same synthetic spectrum with different combinations. There are others that were using, I think, no, the wavelength, maybe from the same spectrum, I don't remember. Maybe some of them were using a broader wavelength.
Oh.
So yes, there are, and then some of them derive iron, but then for other methods, what you get is global metallicity. And this is something we have seen for the end dwarfs. When we talk about iron, it's not the same, or when we talk about metallicity, maybe it's not the same, because in end dwarfs, for example, it's much easier to measure oxygen, and then you have much more abundant oxygen than iron many times. So then when you do this global metallicity, then it can be different than the global metallicity of the FGK stars. So that's all these things that contribute to have also these differences.
Okay, thank you.
Yeah, it's crazy. So if you see something about metallicities of end dwarfs, don't trust too much. At least, I mean, if you compare peers to peers within the same study, you can, they say this study is more metallic than this one, yes. But then when you compare different literatures, then it's complicated, yes.
Hi, Elisa. I would like to go back to the plot you were discussing with Paco about the mass fractions of iron and in the star and the planet. I was wondering, is there, I guess the answer is no, but is there any system when you observe several planets and you co-add the iron mass fraction of you observe in all the planets so that the average would match the star? Because I guess the composition of the disk is what fits the composition of the planets and the star.
Yes.
And if you get different compositions between different planets, it's because of mass segregation and evaporation of
I don't think
volatiles?
we don't have multiplanetary systems here. So I don't think they have done this test, or maybe co-adding if it will be the same as the star. But the idea is that we are using abundance ratio. So it's not the total amount of metals. It's the ratio of one to the other, or this iron mass fraction, with respect to the total. So this is the iron with respect to everything, to water, silicates, whatever. So then since these are ratios in principle, as soon if these planets have been formed up to a given distance from the star, the ratios should be similar. Then if they are formed farther away, then the abundance ratios can change. There are some refractory compounds like calcium, aluminium, that they survive closer to the star. So for example, if you form an exoplanet much closer to the star than the Earth, for example, then maybe you can expect to have higher values of these molecules. This is what I saw in this other work. Here they have much more, the chemical model is much more complex. And then they were showing that depending on the distance to the star, then you can have this difference. But these are, when you are talking about ratios, then it should be constant up to a given distance.
Thank you.
You have time for a couple of questions more, yeah?
Hi, Elisa, great talk. I thought it was super interesting. I wanted to come back to these lithium depleted solar type stars, I thought this was super interesting. Now I wanted to point out that I think mergers can also do this, right?
Mergers.
Yeah, mergers can also severely deplete lithium.
Yeah, there is an explanation. Yeah, one of the explanations is that if you find binarity signals, then you can see that there is a transfer of lithium. Sometimes they check if there is also enhancement of S-process elements, because if there was a merger of an evolved star in the HEV, then you can also get this neutron capture and have higher values. But then there are some that they don't have binarity signals to produce this enhancement of lithium. So then it should be something internal, or yeah.
Cool. Yeah, but my question was, do we have any idea of the rates that contribute to the lithium depletion in these met sequence stars, or the solar type stars?
You mean the ones in the left?
Yeah, or the different contributions between things like mergers and planet engulfments.
No, in the ones in the left, these two plots in the left are for solar type stars hosting exoplanets only in the solar range of temperatures, because it's around 5,700 Kelvin, because when you have cooler stars, the envelope is very thick, and then it doesn't matter if there is an exoplanet or not, or whatever happens, everything is mixed, and the stars, as soon as they start in the main sequence, all the lithium is depleted. On the other hand, when you have hotter stars, the envelope is very thin, and then the movement of the envelope doesn't reach to mix the lithium that is in the surface to the interior. So it's only in this temperature range where something extra can happen and can produce this lithium depletion. And this is what is believed, that exoplanets could be one of the causes, among others, to produce this depletion. And it's what I mentioned, this episodic accretion of, if you have very violent episodic accretion, you can destroy lithium through mixing. Or if you have, if your disk lifetimes change because you have a planet, a disk around the star and a planet, it can affect the angular momentum. And then when you affect the rotation of the star, then this rotational mixing, which is one of the ways of mixing lithium, it can be stronger, and then you can destroy the lithium. So in this case, there are no mergers involved.
And is there any idea of the frequency of, how often does planet engulfment happen? Is it like super rare, or are we expecting it to be?
So in the solar neighborhood, with the samples we studied, then we saw that most of them were depleted, only in this temperature range. But this was the sample we were taking. So these are samples that come from exoplanet surveys, and then they are a bit cleaned before. So you remove very active stars, you remove very young stars. So we cannot test this at young ages, for example. Lithium is one of the main factors that depletes lithium is the age. So as the time passes, the lithium is destroyed. When you go to very young open clusters, then you can see lithium there even in cool stars. So it will be ideal, but I think it's impossible to do, to compare this lithium in stars hosting exoplanets at very young ages to see when you start to see this effect. But I don't think this is possible.
Thanks.
Any more questions in the room? So I think we have some questions on Zoom.
Yes, there is one question in Zoom, which is you mentioned that age and metallicity in stars is not strongly correlated. In your plot, however, the highly enhanced alpha element stars, the name might be different, do seem to form a linear sequence. Can you elaborate on that? Is it a saturation effect of metallicity for a specific age?
I'm not sure I understood this saturation effect. So maybe they mentioned these red stars that all have these 12 gigayears. So these are the thick disk stars, and we know for sure that they are old. Of course, the isochronous method has its limitations. No, you have to put a maximum age, no, when you do it. But it's clear that they are very old. If they are not 12, they will be 13 or they will be 11 gigayears. Where we see the difference is in these ones. In these ones, the high alpha meta rich stars, that they are older, but they don't reach to the maximum. I don't think there's a saturation effect. So they are around 9-8 gigayears, and they are clearly older than these ones. This is clean also with ages less than 1.5 gigayears. And then you see this gradient. So it's both things. Its age is higher, and also the abundances are higher. So that's why we believe this population is different, but it's not clear whether some people say that this is an extension of the thick disk as higher metallicity, so they are stars from the thin disk for the thick disk, or maybe these are stars that are more enhancing these elements because maybe they were coming from the interior of the galaxy and they radially migrated. But I don't think it's clear the origin of these stars, and also because they haven't been observed in so many surveys. I don't think there are many studies trying to understand the origin.
Yeah.
This is an old work, so I really don't remember. I didn't follow this in the last years. I don't know if any recent work talk about this.
She said that she is asking about the red points in the left plot.
Okay. These are the thick disk stars. Okay. Yeah. These are isochronal ages, right? So it's what I said. They can be 12, they can be 13, they can be 11. But they are very old, and they are thick disk stars. They are cooler also generally. So it's like we don't care so much the exact age. It's just to distinguish the populations. I don't know if this answers the question.
Okay. So thank you very much, Elisa, for your talk and also for answering all questions.
Okay, thank you.
Thank you.